In this video, we shall continue our discussion of distributions related to the normal distribution. Here we shall talk about a distribution called the F distribution. To define it, we start with two independent random variables x and y that have distributions chi-square m and chi-square n. M and n, as usual, need not be integers, but in general, for most practical applications, they are. And remember that x and y are assumed to be independent. Then I shall construct a new random variable out of them. X divided by m, the entire thing divided by y by n. So I am taking each chi-square random variable, dividing it by its degrees of freedom, and then taking the ratio. Then this is the random variable, and we know all random variables have their own distribution. So this has a distribution. The distribution of this will be called F distribution, where m and n are both its degrees of freedom, and to distinguish them, m will be called the numerator degrees of freedom and n is called the denominator degrees of freedom. Be a little alert that if you just simplify it, you will notice that n will actually go upstairs and m will come downstairs. But I talk about numerator and denominator because they are associated with the numerator random variable or the denominator random variable. As I have already mentioned, in case of the t distribution, this indirect definition in terms of the chi-square distribution is all that you really need to remember for most practical applications. However, it is good to know that F has a density and we can actually work it out. Pretty simple, because x and y are independent, so I can write down their densities and I know how to apply the quotient formula, and from that we can work the density of F m comma n. The density of x you can easily write down because chi-square m is nothing but gamma half m upon 2. So you have this density. Similarly, y has density, this particular thing. Now we are going to find out the density of, we'll forget about the degrees of freedom for the time being, of just x upon y. And we shall of course employ our quotient formula that we had derived earlier when talking about Jacobian. So this density will be given by integral from 0 to infinity. Remember, all these things are actually positive quantities. U times fx zu, fy u du. Since you are integrating over u, the entire thing will be function of only this z. So let's now plug the formula for fx and fy and let's see what comes out. I have integral 0 to infinity u. Now I am going to write down the formula for fx. Zu to the power m by 2 minus 1 e to the power minus zu by 2. Now I shall bring in fy e to the power u to the power n by 2 minus 1 times e to the power minus u by 2. Direct copy it from here. Now since we are doing the integration over u, you will find some z factor that can be taken out of this, and incidentally I definitely have some constant over there. So constant times z to the power m by 2 minus 1. Don't absorb this in the constant. This comes out because it is free of u. But this cannot be absorbed in the constant because it still involves z. U to the power m plus n by 2 minus 1. You get 1 u here. U to the power this here and u to the power this here. So you have m by 2, n by 2 and minus 2. But one copy, so you get only minus 1. Then e to the power, you always have minus u by 2, and here it is z and here it is 1, so z plus 1, u by 2, and finally a du. And we quickly recognize this form again of the gamma integral form. So this will be the constant and this part as before. This essentially gives you that gamma m plus n by 2, and this thing to the power this alpha, and that is in the denominator, so you have minus this. So this comes from the same trick as we used in the last video of integrating the density of gamma. So you get this thing. And incidentally, the entire thing works only when Z is positive, because this is positive, so this has to be positive, and all throughout I just assume, though U is positive, I also assume that ZU is positive. That's why I could use this formula. So I am assuming that Z is positive, and if Z is negative or 0, in that case this term will just become 0, so the entire thing will become 0. Now remember that our ultimate goal was to find the density of this. This is very much like Z except for these degrees of freedom things. So this is actually n upon m times Z. I know the density of Z, so it is very easy to find out density of that, a trivial Jacobian formula application. So the density of this quantity, which is density of the Fmn distribution, is given by Fx is a constant times x to the power m by 2 minus 1 times mx plus n whole to the power minus m plus n by 2 when x is positive and 0 otherwise. Of course, you can keep track of the constants all throughout our derivation to learn what is the exact form of the constant. It is difficult to guess how the density will look like just by looking at this formula. So I will just tell you how it looks like. So first of all, it will always be supported on the positive side. This is 0 over here. And thanks to this term, you will expect that this will be equal to 0. Of course, here I am assuming that m by 2 is greater than 1. So it just thumbs up somewhat like gamma, and then it decays. So this will be the typical form if m by 2 is greater than 1. But if that falls below 1, in that case it will go up or hit at some finite height. But for most practical applications, you will find that m by 2 will be actually greater than 1. So this will how the density will look like. In this exercise, I give you two random samples. x1 to xm is a random sample from normal mu1 sigma square. y1 to yn is another random sample but from normal mu2 sigma square, and these two are given to be independent. Mu1 may or may not be equal to mu2. Sigma square is the same for both of them, and that's positive. What you do is you compute the sample variance of the xi's and the sample variance of the yi's using sample size minus 1 in the denominator. Then you form the ratio. The question is, what is the distribution of this ratio? Obviously, you are not required to go through all sorts of Jacobian computation. You should be able to express it very easily in terms of the F distribution.